So I've been having a lot of conversations with people about capturing heat from composting, as well as some of the toxic gases that can result from that. So I reached out to one of my colleagues from UNH, Sazan Rahman, to get some updates from an ongoing project at UNH that seeks to capture heat from compost for use in greenhouse grown vegetables. So this work is building off of long-running compost research at UNH. If you think about how most composting is done, we're usually turning those piles in order to get all of the organic matter, all of your greens and your browns, to mix that all up, have oxygen, moisture to feed the microbes that break down that material into beautiful, beautiful compost. Work from Dr. John Aber's lab investigated something a little bit different called a static aerated pile. So rather than having to turn it all over, having a static pile that you aerate with oxygen, so that specifically dairy farmers who are producing this stuff in a year-round system to turn that waste product into a useful product and also capture a little bit of heat while you're at it, that could theoretically be used to heat animal barns or anything else that was going on during the winter. I'm including a video, a little YouTube video in the show notes from that facility in Durham. It's a very exciting concept, particularly those of us who have a lot of excess manure hanging around. UNH, not only does it pride itself on sustainability, it also prides itself on having plenty of hands-on activities for its students. So there's lots of research animals there, animals for their animal studies programs, for their equine programs. So the professors there have access to plenty of feedstocks for compost research. And Dr. Rahman and I certainly hit the ground running and immediately get into the weeds about this topic because it's something we both obviously find very interesting, and that is growing food inside year-round. And because we hit the ground running, I do feel like I need to give you a little bit of primer, a little bit of terminology before I jump into my interview with him. Folks tend to use the term high tunnels in greenhouses interchangeably in many circumstances, and we do that a little bit. But in general, I tend to think about a high tunnel as a pretty low-tech structure over ag land. So you're planting your food crops right in the ground. You usually have an unheated structure over that, and it provides a little bit of protection. When you're talking about a greenhouse usually has a floor. You're usually growing in a container, and you have a lot more control about light, temperature, humidity. You're usually trying to keep that right in the sweet spot of growing conditions. Nowadays, we are starting to see more high tunnel growers adopt some of the technologies that we usually associate with greenhouses. We're getting a little bit fancier. We're really pushing the envelope as far as having year-round production so that you're managing excess heat in the summertime and adding heat in the winter in some cases. You can definitely see where the technology is between low-tech high tunnels and high-tech greenhouses. It's kind of starting to blur a little bit. In my conversation with Dr. Rahman, he talks about a Quonset-style greenhouse. So he's talking about a pretty high-tech greenhouse with lots of control over the abiotic conditions, trying to maintain pretty consistent conditions, but it's a Quonset-style greenhouse, so it kind of looks like a high tunnel from the outside. And he says that he is maintaining pretty consistent temperatures for a lettuce crop, and he does talk in Celsius, 18 to 27 degrees Celsius. So here's a little memory tool for anybody who isn't used to using Celsius in their everyday life. 30s are hot, 20s are nice, 10s are cold, 0 is ice. So if you think about that from a plant point of view, that makes a lot of sense too, especially a cool season crop where we're thinking about like 18 to 27 degrees. That's nice, right? So that's like a 70-degree day. 30s are typically too hot for these plants to grow. 10s are too cool for growth for the most part, and you will start seeing crop injury once that temperature drops below 0, once it gets too freezing. Also, want to highlight that Dr. Rahman is an engineer. So he has to do a lot of terminology code switching when he's talking to plant people like us. Every once in a while, he uses some terms that I, as a biologist, feel compelled to correct. But I want to give credit where credit is due. He's an engineer. He doesn't need to have extensive knowledge about the plants that are living inside of it. And most engineers don't even bother. So we're just going to be cool about it. And I'm talking to myself. So I might flash a note on the screen when I think there might be a clarification necessary. But specifically, he will sometimes refer to pathogenic gases when he means phytotoxic gases. So for him, he's just thinking about gases that cause plants to get sick. For me, I am a biologist, so I'm compelled to point out that a pathogen is typically an organism that causes a disease. So a pathogen is like a fungus or a bacterium or a virus that causes a plant to get sick, and he's using a more generic term. Every once in a while, high humidity, so excess moisture in the air, will exacerbate diseases caused by pathogens in the biological sense, but those pathogens would not be moved in the gases we were talking about. They would come in on their own ways, and then high humidity might make them worse. So that's a nitpicky point, but credit where credit is due. It is nice to see engineers thinking about plants from a very thoughtful point of view. So listen to our conversations. Very cool.
This is MD Sazan Rahman. I'm an assistant professor at the University of New Hampshire in the Department of Agriculture, Nutrition, and Food Systems.
Well, let's talk about the manure heating project, because on its surface, it sounds like, oh, what a fantastic idea. But the more I read about your project, I go, oh, this isn't just about heat. This is about humidity too. So start from the beginning. Tell me about the manure heating project that you're working on at UNH right now.
For the manure project, we were kind of having this idea from some preliminary data from John Aber. So he is a retired professor at UNH. He was the one who first tried some aerobic digestion, and he found out that the amount of heat we can produce from aerobic digestion is immense. Like, you can utilize that heat for any commercial purpose. So then he was retiring, and when I joined 3 years ago, and we had a really good meeting, and all of a sudden he was like, Sazan, you work on this field by training, you're an engineer. Can you try this? And I applied for our agriculture experiment station, AES grant, that the foundational money. What we are doing right now, we are trying to heat up a standard size of high tunnel. It is a greenhouse style high tunnel that I can say, which is 60 by 30. This high tunnel, which is, I would say, one of the most popular high tunnel size in northeastern USA. We were trying to find out the year-round heating demand and other microclimate demand of that greenhouse, and then we start comparing that demand with manure-based or aerobic digestion-based heating, or whatever energy that we are having from it. And I hired one of my PhD student, Hampshire Rahman, and I dedicated his full time to this. The first phase was just doing all the calculation and simulation. We were kind of simulating a stockpiles of manure with different blending and composition, and we're trying to figure out how much heat we can produce. I would say it's a vaporized heat. It's a heat with pathogenic gases, but still we want to know that BTU amount or so kilojoule amount.
That was my question for you. Is how do you measure heat? You said you were comparing that to the needs of a regular high tunnel in New Hampshire. So how much you would need to supplement heat in a high tunnel is can you ballpark estimate how much heat a tunnel grower is using?
Yeah, so I can always break it down into different parts. So the first part was to do the energy assessment or heating and cooling load requirement for a standard size high tunnel in New Hampshire. That was the first part. So what we did, we tried to simulate the environment in ANSYS, and then we draw the high tunnels. We just estimate some kind of infiltration, some kind of leaking. Leaking was zero, but infiltration, let's put it that way. Infiltration through its door and through the vents that happen both sides of the end wall. So we consider that, and then we go through the year-round environment and the solar radiation. And we did it in I would say 3 different manners. One, through the empirical formula. So people has some estimation of different size of queen set type greenhouses plus high tunnels. So there are some empirical formula there. So we go through that formula, and then there are some standard table based heat requirement calculation for queen set type greenhouses. So we go through its cover material, we choose its cover material, and then size, then the location and everything. We estimated the wind velocity and what can be the lowest possible temperature. So transits and energy flow, what it can do, you can draw the same shape of high tunnel on energy flow or transits, well, energy plus.
Okay.
So an energy plus is the prescribed one from USDA, and it's a free software. So if you get into Energy Plus, you can see their user interface. You can draw the exact same high tunnels, and you can put the coordinate, and they will import the historical data of that location, like what is the lowest possible temperature, what is the highest possible temperature. Then you have your own coordination for your high tunnels. So you put them all.
Does that allow for variability in like how many cloudy days or sunny days? You're saying like if every day was the coldest it could possibly be, and then every day was the warmest it could possibly be, and that's your range?
No, it doesn't go by this way.
Okay.
So it goes by the historical data.
Okay.
So the historical average of last 10 years, you can go that way.
Oh, cool.
So historical average of last 5 years, historical average of last 10 years. So historical average of, let's say today is May 22nd, right? So let's say historical average of today's temperature, maybe the highest temperature is 22 degrees Celsius. The total sunshine, maybe 14 hours. And you know when the morning is coming up and when the sunset is happening. And you know how much cloudy it can be, or what is the probability of rain. So you know from that historical data, we can only trust on that data because no one can talk anything about future, right? Adding those all values with solar radiation and everything, then you can have a heating requirement, like how much the heat can be generated underneath of the cover and how much you need to supplement there.
You mentioned that you're doing hydroponic production, so your heat needs are probably a little bit higher than some of the high tunnel growing conditions that I'm used to, where I'm used to people who are growing very cold tolerant crops, where you probably could allow that space to get down to nighttime temperatures for like, you know, a couple hours, like having a couple hours of freezing temperatures is going to be fine. But it sounds like the operation that you're working with, like you do need to keep your nighttime temperatures above some threshold. What are you shooting for?
So when we calculate the energy demand, we go with a set point, and that set point was set up for lettuce because that is our model crop to try here. So we go with 18 degrees Celsius nighttime. I'm talking about degrees Celsius. So be a little cautious about my numbers.
But that's 18 degrees warmer than freezing. So.
Oh, way more than freezing.
Yeah, much warmer than freezing. Yeah.
Yeah. So 18 degrees Celsius, because we are calculating the demand. So if it is overestimated, it's fine. We don't want to underestimate. So when we're calculating the demand, we go with 18 and 22. So that is our lower and upper threshold in terms of heating requirement and cooling requirement. And I think for the cooling requirement, we go even beyond because 27 was the higher threshold, but the standard set point was 18 and 22 for night and day. So that was the set point to see how much cooling is happening in the very cold winter time, and how much heat we really need to get to that point.
Awesome.
So that was the estimation, and then we estimated per hour the kilowatt demand per hour, or kilowatt hour demand, or kilojoule per second per hour, whatever. So that demand we converted that into BTU as well. I don't remember the BTU number in my head right now, but we calculate that, and then we start designing the aerobic digestion system. So then our whole challenge was how much area or how much volume of manure we need to handle to supply that demand. So John Aber's all his research work, and he had a really great work because his student got PhD on that. So he has all the data, and we get through all the tables and his appendix to figure out how they set it up, how they really stockpile manure, how they change manure, what was the timeline, changing the stockpiles and everything, how was the bay size, and how they really feed the pipes underneath of the bay to suck all the air, which is vaporized gases. So I would say we have an industry partner, Agrilab. We communicate with them, and they have some expertise. They still also have some gaps, which we'll be addressing through our research, but they were providing some data too, like this amount of manure you normally need. If you blend the manure with cow and horses together, maybe with the changing of composition, you might have a different kind of heating provided from the stockpiles.
And that might be just because their diets are a little bit different, and they're like what goes in and what comes out.
So the amount of moisture into that manure, plus the bedding of the horse and bedding of the dairy or cows, they're not the same. So the bedding materials that we use for both of the animal barns. So if you stockpile them together and you start aerating through that the whole stockpile, the heating or the energy supply will depend on the whole composition. So when we get through the composition level, it's really surprising to see like how they really change per I would say per unit amount of the composition. So it can be per kg, per ton, or per stockpile, whatever. So we get through that point, and then we decided that a 30 by 30, a 5 feet height, that could be a good volume for a standard high tunnel size. So far, that is our estimation. However, last winter, the winter that we just passed, it seems like we underestimated because the winter was really...
It was really cold. It was a tough winter.
We use supplemental heating because our compost bay is not ready yet. So when we use the supplemental heating, we use the heater and we count each and every energy and fuel spent by the heater. So when we see that in actual case, we were growing lettuce inside, and whatever energy we spend is little, well, not little, I would say 20% above our estimation. The estimation was not good enough for rush winter like this winter this year. Or you can put it other way around, is like leaking or infiltration on the high tunnel.
Okay.
Because when you do a simulation, you cannot compare the real time leaking with simulated leaks or simulated infiltration. Let's say it's a day with snowstorm. The wind is really high. Temperature is really cold. Like if the snow gets stockpiled around the tunnel, that's a different kind of heat transfer. Snow often works as an insulator. At the same time, it can add cooling, or I would say it extract heat, the same thing. So it extract heat in a conduction manner. So if you go with the basic heat transfer idea and you are doing simulation on the computer, you allow convection there, but in real time you see conduction from a really cold plate, which is the snow.
But that gets back into the goal, which was to keep a steady temperature between 18 and 21 degrees. If your goal was to, minimize the number of hours of freezing temperature, that snow would have a different role, right? So you're going to learn a lot from this research project, but it sounds like you're also going to walk out with a lot more questions that you want to test in the real world in the future, right?
Yeah, so every stage, like last winter was our growing stage. On the growing time, on every stage of the crop, we had multiple number of questions that we may need to address in the next growing cycle. So that is, at the same time, even if it is not maintaining 18 degrees Celsius, if we need a little bit of supplemental heat, we can at least tell to our growers that this size, you may need to extend the size 10% more. So 30 by 30, maybe you can make 35 by 35. We can provide the solution no matter what, but the questions are coming. Yes.
Is there anything else you want me to know about, the things that maybe you didn't know before you started this project? Like I had a really fun conversation with John Aber when I first joined UNH, and he was very much like, oh, are you going to be the guy who takes my research and runs with it? So he must have been so thrilled that you walked into his door because he was waiting for you, right?
Yep.
So,
Yep.
like, what are the things that you've learned as John passed that torch onto you that you were surprised about?
Well, I think the way he did it is already novel enough and surprising enough.
Yeah.
Because he needed quite a low tech, and he was like, well, you don't need anything, you just suck the air from it.
Yeah.
That's it for heating. But for applying that heat to greenhouse, that makes things little complicated. If that heat comes up with different kind of gas, maybe our plant doesn't expect that. If you use it for some industrial purpose, it's fine. But for going inside a compartment and you're sending that heat directly to that compartment is a little challenging. The thought comes in like how we really wanna transfer this heat into the high tunnel or into the greenhouse. If it is an indirect system, like if you use a heat exchanger or if you use a heat pump to transfer this heat to your room, that is fine. In one point when he was sending that the whole gaseous composition into the air, he was basically passing that through a stockpile of wood chip, just not to make a lot of smell or a lot of pathogenic stuffs inside. And that wood chip stockpile surprisingly reduced the amount of smell. And then when I and Hafizur, my student, when we were working together to find out the way to transfer heat from that manure stockpile to the greenhouse, we are thinking of both direct method and indirect method. So fortunately, that high tunnel is already have an embedded heat pump to provide indirect heat to the high tunnels from those compost or compost bay or those manure aerobic digestion system. Other side, when we're thinking like, well, this is not a good thing for our small and medium farmer to put a really big industrial heat pump or a heat exchanger. We want to make it really low tech. So then that time we start designing that biofilter. Like as we get the hints from Professor Aber saying that wood chip works to reduce the odor and smells. We start digging more into the biofilter, and now the design is ready. So we designed the biofilter to remove all the pathogenic gases, some amount of vapor because we don't want really humid air to get in directly into the greenhouse, and some of the other pathogens will be converted into regular gas. So let's say carbon monoxide may be converted into carbon dioxide. So nitrous oxide may be NO2, nitrogen dioxide. We designed the biofilter with 3 different layers. So the first layer, they'll be mixing with some manure or bioactor microbes to convert them in one way or others. And then the other layer is again the wood chip and biochar. So that wood chip and biochar blend, there will be some catalytic converting stuffs like the like you know the catalytic converter of the car, right?
Yeah.
So that changes the NOx into the regular gases. We don't want to go with that high-tech system, but we'll use some of the catalytic powder into our blends of the biochar and the wood chip. So that is the second layer. And there will be a third layer of different kind of fiber like coconut coir and some other biofibers to reduce the humidity, plus to do some more conversion of the pathogen gas into the regular gases. So that is the plan for now. We design it in such a way that the air is uniformly distributed throughout the biofilter. From there, are thinking of the biofilter of 9 feet by 9 feet and 3 feet height. And it will be fully sealed because we don't want any heat to go out in the winter time. And we're going to utilize the heat to heat up our greenhouse and hydroponic system.
So gases like nitrogen, like what about methane? Are you measuring methane? Is that another one?
We'll be measuring all kind of ammonia, methane, hydrogen sulfide, NOx, SOx, those all before and after the biofilter.
So right now, your 2 approaches is like completely cutting out any possibility of that toxic gas getting into the greenhouse because you're heating.
That's the hope.
because you're heating water and the water is then heating that. And then your other way is using a biofilter that has all these layers of security. So you're putting all these different things in there just to see if you can achieve the same thing. I'm wondering, like, do you see a reality where somebody could make their own biofilter? This seems very accessible.
Yes. So, as you mentioned, the first approach will be sending the heat to water. The water reservoir will reserve the heat, and a heat pump, which is already embedded inside the greenhouse, will transfer that heat anytime we need from that water. So that is one way that is safe.
Yeah.
So there is indirect heating. No composition from that manure or from that manure-based vaporized gases is coming into the greenhouse. That is safe approach. The other approach, which is easy, which is really cheap, but whether it's safe or not, that is the question. So on that approach, if you think about the material that we use, it's a wooden box, and then you have biochar, dry manure, you have a different kind of wood composition, like wood chips and wood powder composition, a little bit of catalytic powder, the powder catalyst, and then again you have all the less expensive or least expensive biofibers. So when where you are making an wooden box, and then you are putting all this layer one on top of another, I would say one is easy to make. Second is really less expensive, like it's cheap, and all the available materials that you can use to put in there. The only trick you need to know is to make uniform airflow inside the biofilter. So that is the main trick, being a grower.
Okay. So I can see where you're refining that method so that it's as foolproof as possible if and when people want to adopt the homemade version, the biofilter. That's very cool.
Yeah.
Cool.
So it's all about the whole plan is all about our small and medium farmers.
Awesome. That's very cool.
That was the whole plan.
All right, I will leave it there for now, but we did have a much longer conversation about humidity, which is definitely a problematic gas if you have too much humidity or too little humidity in a place where you're growing plants. That's a topic for another day. It's definitely one of Dr. Rahman's specialties, so you'll be hearing more from him about this, and particularly because his lab is going to continue to find new and innovative ways to handle high humidity using very smart, low-tech approaches that are appropriate for low-tech growing practices like growing in high tunnels. So watch this space, and thanks so much for listening.